Welcome to Brain Vision.
Hi everyone, so what we have is an ideal gas that is adiabatically expanded through a turbine and work is extracted from this turbine. We know that this ideal gas enters the turbine at a pressure of 900 kPa and at a temperature of 1200 Kelvin, and it leaves at a temperature of 800 Kelvin. The amount of work that is extracted is equivalent to 650 kilowatts. What we're asked to solve for is the volume flow rate of this ideal gas through the turbine. So first what we're going to do is go ahead and state our assumptions. So we're going to assume that this is at a steady state operating conditions, so things are not going to be changing with time. We're also going to assume that any changes in kinetic energy and any changes in potential energy are negligible. And we're also going to assume that since this device is adiabatic, that heat transfer is also negligible. That's cute. Next, what we're going to do is we're going to write down the properties of the ideal gas that were given to us. So we're given that our gas constant is equal to 0.3 kilopascal meter cubed all over kilogram Kelvin. We're also given that our CP value is equal to 1.13 kilojoule per kilogram degree Celsius. And we're given that our CV value is equal to 0.83 kilojoules per kilogram Celsius. So we're going to define our system as the turbine, and that's going to also be our control volume. So when we do our energy balance, we can say that the rate of energy coming in minus the rate of energy leaving is equal to the total rate of energy change in the system. However, as we stated before, we're dealing with a steady state operating condition, so therefore this will be equal to 0. So we can say that the rate of energy coming in is equal to the rate of energy leaving the system. Now we can further expand upon the constituents of these terms and say that the total energy coming in is going to be m dot times the enthalpy is equal to the shaft work plus the exiting enthalpy. Now what we can do is rearrange these terms to solve for the mass flow rate, and we'll see that m dot is going to be equal to the total shaft worked all over H1 minus H2. Now since we know the CP and CV values for this ideal gas, we can go ahead and write enthalpy in terms of CP and temperature. So we can say this, that m dot is equal to W dot out all over CP T1 minus T2. And for plugging in for these values, we see that m dot is equal to 1.438 kilograms per second. Now we can use the ideal gas law to solve for the specific volume, and just by rearranging the ideal gas law to solve for specific volume, you can say that V1 is equal to RT1 over P1, and for plugging in for these quantities, we see that the specific volume is equal to 0.4 cubic meters per kilogram. Now we can easily solve for the volume flow rate by simply saying that volume flow rate V dot is equal to m dot times specific volume 1, and this gives us a total volume flow rate of 0.575 cubic meters per second. And that is our final answer.